Percent composition is important in chemistry. It is useful for elemental analysis and for identifying unknowns. We need to know the molar mass first, which I explained in an earlier video and I'll link to here. Percent composition is simply the percent by mass of elements in a compound. Let's use the example of methane. In my earlier video on molar mass, we saw that the molar mass of methane is 16.05 grams per mole. This is from 12.01 grams from 1 mole of carbon and 4.04 grams from 4 moles of hydrogen. To find the percent composition by mass of each element, simply take the mass of each element per mole of compound and divide by the molar mass of the compound. Multiply this ratio by 100 to get the percentages. Hydrates are compounds in which water is incorporated into the structure. This means that when a crystal is formed, water molecules occupy some of the lattice positions. For hydrates of ionic compounds, a water is written after the ionic compound. The coefficient in front of the water shows the ratio of water per formula unit. Hydrates can also be heated to yield what's called the anhydrous compound. To name a hydrate with an ionic compound, simply name the ionic compound and add the name hydrate to the end. Add a prefix to indicate the number of moles of water per mole of compound. Here, the name is copper 2 sulfate pentahydrate. Our other examples are cobalt 2 chloride hexahydrate and barium hydroxide octahydrate. For any mass analysis, you must include the mass of water. For example, the molar mass of copper 2 sulfate pentahydrate is the molar mass of copper 2 sulfate plus the mass of 5 times the molar mass of water. Molecular formulas are generally introduced to chemistry students as the number of atoms of an element in a molecule. This is true, but chemists generally report amounts of substances in terms of moles. Another way to define the molecular formula is the exact number of moles of elements per mole of compound. Methane, for example, has 1 mole of carbon and 4 moles of hydrogen per mole of methane. Ethene has 2 moles of carbon and 4 moles of hydrogen per mole of ethene, while benzene has 6 moles of carbon and 6 moles of hydrogen per mole of benzene. Note the definition of the empirical formula. It is the simplest whole number ratio of moles of element in a compound. In other words, how do the moles of elements in a compound compare? In methane, there is 1 mole of carbon per 4 moles of hydrogen. The empirical formula is CH4. Yes, the molecular formula and the empirical formula can be the same. But look at ethene, C2H4. The ratio of 2 carbons to 4 hydrogens can be simplified to 1 mole of carbon for every 2 moles of hydrogen. The empirical formula is CH2. And for benzene, the carbon-hydrogen ratio of 6 to 6 can be simplified to 1 to 1, and the empirical formula is CH. Because the empirical formula is the simplest whole number ratio of elements in the molecular formula will always be some whole number multiple of the empirical formula, represented here by the letter N. The ratio N represents the molar mass of the molecular formula divided by the molar mass of the empirical formula. The molar mass of the molecular formula must be given in the problem. Here is an example. The empirical formula for a compound is CH. That is, there is 1 mole of carbon per mole of hydrogen present in the compound. The molecular formula is 104.16 grams per mole. Find the molecular formula. The molecular formula is equal to the empirical formula times the ratio of 104.16 over 13.02. The molar mass of the molecular formula is given to us in the problem, and the molar mass of the empirical formula is 13.02. This is because it comes from 1 mole of carbon and 1 mole of hydrogen, which are 12.01 and 1.01 grams per mole respectively. This ratio is equal to 8. We can distribute the 8 equally to each element and find the molecular formula, C8H8. Let's determine an empirical and molecular formula from mass percents. Mass percents can be determined from mass analysis using combustion experiments, while molar masses of samples can be found from mass spectral analysis. In this example, a sample of compound contains 30.46% nitrogen and 69.54% oxygen by mass. The molar mass of the compound is found to be 92.02 grams per mole. Determine the empirical and molecular formula. Let's determine the empirical formula first. This is the mole ratio of nitrogen to oxygen. Then we can determine the molecular formula from the empirical formula. Because we're dealing with percentages, we can start by assuming that there are 100 grams of compound, because each percentage can be converted directly into grams. That is, 30.46% nitrogen is 30.46 grams of nitrogen, and 69.54% oxygen is 69.54 grams of oxygen. Recall, the ratio of masses don't really matter to us. What does matter to us is the ratio of moles. So next, each mass can be converted to moles using the element's atomic weights. The moles can now be compared. Remember, we want the simplest whole number ratio of moles between nitrogen and oxygen. So we can obtain this by dividing by the smallest moles. Here, we'll divide each value by 2.174. The ratio of nitrogen moles to oxygen moles in the compound is 1 to 2. And the empirical formula is NO2. Going back to our problem, we have determined the empirical formula. Now, let's determine the molecular formula. We need to multiply the empirical formula by some multiple n. N equals the molecular formula molar mass divided by the empirical formula molar mass. Here, the molecular formula molar mass, 92.02 grams per mole, was given in the problem. The empirical formula molar mass is the molar mass of NO2, 46.01. We can distribute the ratio of 2, and the molecular formula is N2O4. Let's determine the empirical and molecular formula from mass percent. A sample is analyzed and found to contain 43.64% phosphorus and 56.36% oxygen by mass. The compound has a molar mass of 283.88 grams per mole. What are the compound's empirical and molecular formulas? Let's find the empirical formula first. When dealing with mass percent, it's easiest to assume a 100-gram sample, because it is convenient to convert percentage to masses. Then we can convert to find moles of elements, then ratios. Based on percentages, a 100-gram sample will have 43.64 grams of phosphorus and 56.36 grams of oxygen. We can find the moles of each element next. This mole ratio isn't the simplest whole number ratio, so we can divide each mole by the smaller value. Notice that dividing by the smallest moles results in a fraction for oxygen. This isn't the simplest whole number ratio either. When a fraction occurs at this point, we can multiply all the moles by a whole number in order to obtain a whole number ratio. In this case, 1 mole of phosphorus and 2.5 moles of oxygen can be multiplied by 2 to give an empirical formula of P2O5. We can now find the molecular formula by finding the relationship between the molecular formula mass and the empirical formula mass. I have earlier videos describing this equation. The empirical formula is 141.94 grams per mole, while the molecular formula, 283.88 grams per mole, was given in the problem. This gives us a ratio of 2. We can distribute the ratio of 2 to find the molecular formula of P4O10, or tetraphosphorus decaoxide. Let's find the molecular formula for a molecule that has more than 2 elements. I'll refer you to my other videos on empirical and molecular formulas for more examples. Caffeine is a stimulant found in coffee, tea, and chocolate. It contains 49.48% carbon, 5.16% hydrogen, 28.87% nitrogen, and 16.49% oxygen, all by mass. And it has a molar mass of 194.2 grams per mole. Let's determine the molecular formula, but first we'll determine the empirical formula, which is the simplest whole number ratio of elements in a compound. We'll first assume a 100-gram sample, which is convenient to convert the percentages into grams. The mass really doesn't matter to us. What does matter to us are the moles of each element present and how they compare. Use each element's atomic weight to convert to moles of each element. Dividing by the smallest moles and comparing gives the simplest whole number ratios of moles of elements in the compound. The empirical formula is C4H5N2O. Now we can find the molecular formula by finding the relationship between the molecular formula mass and the empirical formula mass. This equation has been explained in earlier videos. Briefly, we can multiply the empirical formula by the ratio of the molecular formula molar mass, which is given in the problem, and the empirical formula molar mass. Here, the ratio is 2. We can then distribute the 2 to get the molecular formula of caffeine, C8H10N4O2. There are techniques available to chemists to help determine empirical and molecular formulas of unknown compounds. Here's an example of a simple combustion device used to analyze substances for carbon, hydrogen, and sometimes oxygen and nitrogen. It helps chemists determine the mass percent of each element in an unknown compound. First, a known mass of sample is placed in a furnace. Upon heating with oxygen, the sample will combust and form carbon dioxide, water, and other byproducts. The products will then pass through a series of filters, including a carbon dioxide absorber and a water absorber. Other filters can be used to capture other products to determine the presence of elements other than carbon and hydrogen. By measuring the masses of the absorbers before and after the experiment, the mass of the carbon and hydrogen in the unknown sample can be determined. Let's do one example. Combustion of 0.225 grams of an organic compound containing carbon, hydrogen, and oxygen yields 0.512 grams of carbon dioxide and 0.209 grams of water. The sample's molar mass is found to be 116 grams per mole. Find the empirical and molecular formulas. Here's the equation, unbalanced of course, because we do not know the molecular formula. But it does illustrate that the carbon from the sample is converted to carbon dioxide and the hydrogen is converted to water. We'll find the oxygen of the sample later. First, let's identify the amount of carbon and hydrogen in our sample. To do this, I'll take advantage of the percent composition of carbon in carbon dioxide and hydrogen in water. I have another video explaining the percent composition by mass. Here, CO2 has 27.29% carbon by mass, and water has 11.21% hydrogen by mass. Multiply the carbon dioxide mass by 27.29%, or 0.2729, and multiply the water mass by 11.21%, or 0.1121. The masses for carbon and hydrogen are 0.140 grams and 0.0234 grams respectively. These are the masses of carbon and hydrogen that came from the original sample. The remaining mass, of course, is oxygen. Subtract from the initial sample mass to find the mass of oxygen. Now we know the mass of each element in the sample. Let's find the moles and the mole ratios of the elements for the empirical formula. The empirical formula is the simplest whole number ratio of moles of elements in a compound. We have the masses, so now we can use the atomic weights to convert to moles of each element. To find the simplest whole number ratios, we can divide by the smallest moles, 0.0039 moles from the oxygen moles. The answers are the simplest whole number ratios, and the empirical formula is C3H6O. Let's find the molecular formula next. The molecular formula is always some whole number multiple of the empirical formula, represented here by the letter N. N is the ratio of the molecular formula molar mass to the empirical formula molar mass. Here, 116 grams per mole over 58.09 grams per mole equals a ratio of 2. We can distribute the ratio of 2 and find the molecular formula, C6H12O2.